Hello, and thanks for coming to my talk. So we're going to talk about fingerprinting encrypted traffic. So I'm Adel, member of the HoneyNet project for about 10 years now, security engineer detecting badness at Google. And in my free time, I'm working on some open source project you can find in my GitHub page and doing some astrophotography, like the photo you see in the last slide. So let's start by defining the problem. Actually, the large part of your network traffic is already encrypted. And it's hard to tell if the traffic we see is actually good, like an engineer searching for cat memes, as it's like a big part of our day-to-day job, or it's like a malicious traffic or someone exfiltrating data from your network or communicating with command and control. So let's see if there's any clues. We can actually use network metadata and potentially fingerprints to make more sense of encrypted traffic. And in this talk, we're going to see if we can use network metadata and fingerprints to profile the attackers and tools, discover hidden connections between the attackers or tools again, or maybe even we can find some cool evasion techniques. So let's see. Just a quick background. This is the basic concept you need to know to understand this talk. So cryptographic protocols need to negotiate some parameters, attributes in clear text. Let me try to explain it in another way, hopefully easier. Assume this is encrypted traffic. We can't really see anything, like we don't really know what's happening, but we can see the handshake here. And by looking at the handshake, we can probably guess it's right, frog and Todd eating cookies. So let's start by an example with TLS. So in TLS, in the initial handshake, we actually have a client hello message, which includes some interesting information, which is clear text. So here's the structure of client hello. And here are some interesting fields we can probably use for fingerprinting, like version, like TLS 1.2, or the cipher suites, which is the most interesting one, because these ciphers are in order of client's preference. So probably we can use this for some kind of fingerprinting. And then the list of extensions. So there are some fingerprinting methods for TLS, but the most common one is JAW3, which is developed by John Althouse and a couple more guys at Salesforce. And it works by extracting and concatenating the decimal value of SSL version, cipher suites, extensions, elliptic curve, which is an extension, and then EC point format. So after we generated this string, we apply MD5, and the result is the hash, which is a unique fingerprint for SSL clients. In this case, it's for Google Chrome. So let's have a look at RDP. And I was thinking if we can apply the same thing to RDP, because RDP is an interesting protocol. It's a common protocol which is used for lateral movement, and also the recent vulnerabilities like BlueKeep makes it more interesting. So there are actually two RDP security modes, standard RDP security and enhanced RDP security. In enhanced mode, we have the following protocols, and the good thing is all these protocols are based in TLS. So again, we can use something like JAW3 to fingerprint them. So what I did was I generated traffics for different RDP clients on different Windows versions, and the result was cool. So as we expect, there are unique fingerprints for each client. As you can see here, this is a fingerprint for RDC 6.1 on Windows XP, or this one is for Windows 10 or 2019, which you can see is the same, because both use the same RDP client. And this one is Poppy's RDP module. As you know, Poppy is an open source implant, so it also has an RDP module, and the JAW3 is unique. So it's cool. You can just use this fingerprint and create a Surikata snort rule and detect it in your network. What if we use standard RDP security? In standard RDP security, we don't have TLS. Standard RDP uses its own custom encryption mechanism based on RSA and RC4 or triple DES. But here we have another interesting message, which is basic settings exchange. This message is encrypted in enhanced mode, so we can't see that, but we can see that here. And there's a message called connect initial PDU, which includes another message, which is GCC conference create request. And this message has 4 structures, as you can see here: core data, cluster data, security data, and network data. So let's have a look at these fields. By the way, you can use these data in core data for hunting. There are interesting things like keyboard layout and some other things which is used for a long time for hunting. But for the purpose of fingerprinting, I used the minor and major version, and from the cluster data, I extracted the cluster flags, encryption methods, and EXT encryption methods from security data, and channel diff from network data. So here's an experimental fingerprinting method for standard RDP security I created, and the same way as JA3, we extract some fields and concatenate them to generate the fingerprint. So major, minor version, cluster flags, encryption methods, EXT encryption methods, and then the channel diff. So we apply MD5, and this is a fingerprint for that RDP client. So in this case, it's Windows 10. This is another interesting example I captured on my honeypots the other day, which is probably RDP scan, which is a scanner for blue chip vulnerability. So if you're interested, because I removed lots of details here, if you're interested to know more about this RDP fingerprinting thing, here's a blog post I published a few months ago. Just scan this QR code. It's totally safe, not a trap. And let's now have a look at some observations. These are actually some logs I captured on my honeypots for about 2 years now. So I started collecting fingerprints for TLS, SSH, RDP, and many other protocols from my honeypots. And I started visualizing them by creating a graph and connecting the source IP to the fingerprints. So in this case, which is for TLS, source IP to JA3. So this was the result. And as you can see here, there are some clusters. Some are normal and the things which are expected, like this. So we have one red node in the center, which is the fingerprint, and many IPs around, which is actually, which means many IP sources or clients using the same tool. So we have the same JA3 for that. And this is normal. We expect to see that. But let's go back and zoom into a couple more interesting stuff. So if you have a look, we have 3 outliers here, which is like 1 or few IPs, and then many JA3s, like 300 or 400 different fingerprints. We have another one here, and another one here. So this one is my favorite one. So let's zoom in and learn more about this one. So let's zoom in. So before go further, something interesting here is that these 4 IPs are different IPs. The scan times are different. Everything is different and random. But you can see here that we can connect these 4 clusters together because of those common fingerprints in the center. You can see that. So because of those, we can connect these 4 clusters together. And that's probably the same actor or different actors using the same tool. We don't know. So let's go deeper and see if we can learn more about this. So let's zoom in a bit more. Yeah. So we found a huge needle in haystack. And these are actually some attempts to avoid TLS fingerprinting by randomizing the client hello fields. And the funny thing is, by doing this, they make themselves easier to detect. And as you saw, it was like so obvious. So let's go deeper and see what's the reason behind these random fingerprints. So this is the Jotry ciphers in the message, and this is like one specific day, and just a few seconds, I've received like 400 different connections. And by looking at the ciphers, you see an interesting pattern here. So the first connection is with some within a specific cipher string, and then another, and then 6 more connections with the first cipher. So as you can see, it's the same as the first one. And then another one, which is an invalid cipher. So we have that here, and then a wall of text, which is actually a huge list of randomly generated ciphers. So the more interesting thing is, in the next slide, you can see the same scan happened like 26 days later again. And the cool thing is, the ciphers are different. The randomly generated ciphers are different, but the pattern is the same. So we can always identify this specific actor or tool because of this pattern. Let's have a look at another example. This is the visualization of data set I had for RDP, for standard RDP security. And as you can see, we again have some clusters here. I'll have a look at 2 more interesting ones. So one is this one. So we have many IPs, but all of them generate 4 unique fingerprints. And when we have a look at the logs, we see that this guy actually randomized the RDP cookie for some reasons, which I don't know. And it's also probably Nmap or customized Nmap. And the cool thing is, we always have these 4 unique fingerprints for this actor. Here's another cluster in that visualization, which I just showed. And this is probably Morto malware. So I had a look at the logs and some features, and I've noticed that it's a Morto malware, and it always generates these unique fingerprints. So it's cool. You can detect Morto malware in your network or somewhere else by just looking at this special fingerprint. So key takeaways: NSM is not dead. Like we can still use network security monitoring for encrypted traffic, and the initial handshake in cryptographic protocol is gold. We can use it for creating fingerprints to identify the clients or servers, and hunt the badness by, for example, looking for rare fingerprints in your network, or maybe looking at like Python, PowerShell, or Go binaries connecting to some weird domains. And you can do that with fingerprints. So you also saw that we can find hidden connections between the actors and tools just by using these fingerprints. So I had a chat with one of these actors, actually. I know one of them. And he said they're doing this for about 4 or 5 years now, but no one noticed that because no one was monitoring like their honeypots and generating the fingerprints for visualizing that. So thanks. That's it. Thank you.